All right, so as starting the new video or time here, or whatever it is, once you're done with graphing and you have to 2 pi, you've completed one cycle of your graph, and really that's all you want is one cycle. If you would continue after this, it would just start tracing over, and we don't want to have that. So our domain, or what we would be looking at here, is we want from 0 to 2 pi. That graphs one cycle, and then we can be done with it. You can also check these on your calculator. So take your calculators out, and with your calculators, our mode now, we want it to be polar mode. Oops. So polar, press enter so that's highlighted, and then you can quit out of that. If we go to y equals, you'll see now that instead of x's, or the x sub 1, y sub 1 for parametric, now we have r, because we know that polar equations are written in this form where r is equal to 3 cosine 2 theta. So then we have 3 cosine. Your 2 theta, whoops, would have to be in parentheses, which your calculator already puts in there. And now when you put in your variable, now it automatically puts in a theta for you. Our mode, which you should have checked, it has to be in radians, which it probably is. And our window setting, we know what this one should look like, because obviously we have it graphed here. So I'm going to go from 0 to 2 pi, which I have, and then theta step, just like when we had for our parametric, that step, I go by 0.1 because that makes it's calculated often enough that it looks like a nice smooth curve. For my x minimums, I'm going to go from -5 to a +5, and for my y minimums, a -5 to a +5. And I already know what the graph looks like, so I know that that should be sufficient. And there is my equation. You can see when it's graphing that we have that little thing scrolling up here, and it ended exactly here and it didn't retrace, which is one thing that I like to see. The other thing is this graph looks slightly distorted because it's not a square, which we'd want it to be. And we know that it's more rectangular, so our our x-axis is longer than our y-axis. If we went to our window setting and we only graph from 0 to pi, now if we graph, it stops at pi, so we only have that portion of it, which this graph isn't going to just start and stop here. There's going to be more curve to it, or it would continue, to the right for a very long time, or to the left for a very long time. So you do want to see if there's more to it there, I guess. And then if you go to, instead of going to 2 pi, let's go to like 3 pi. Now if we graph this, you'll see that it's up here, it's scrolling through things. Okay, now you can follow on your calculator that it starts retracing, and we don't want to retrace. We only want our domain where we have one graph of it, only one cycle. So calculator is always a nice option too, to check it and see what you're doing, but I will make you complete the table as well. We do have slope and tangent lines in here. I think at the beginning I said we don't have a lot of calculus. There is a little bit of calculus in this one. Obviously we know if we want the slope, that deals with our derivative, and tangent lines go right along with slope. So f is a differentiable function of theta. Then the slope of the tangent line to the graph of r equals f of theta is the following. The easiest thing to do is to convert our polar equation to a parametric equation, and then we'll take our derivative from there. So it seems kind of goofy, but it's a really easy way to do this. So right now we know that our equation is r is equal to f of theta. So we just have r is equal to something in terms of theta. Well, if I want to write a parametric equation means I have to have two equations. What is x equal to and what is y equal to? Well, going back to the polar, we know that x is equal to r cosine theta, and we know y is equal to r sine theta. Well, what this allows us to do is our polar equations are given in terms of r, So I can take this, whatever r is, and plug it in place of there. So it makes it really, really easy. Then I know how to take the derivative of a parametric equation. So if I take the derivative of a parametric equation, this r, remember, is going to be something in terms of theta. So I can write this out and say, well, I know it's f of theta times cosine theta in the long run, but really that f of theta is equivalent to r. And then same thing, y is equal to f of theta times sine theta. Now when I take the derivative of y with respect to theta, that will be the numerator, divided by the derivative of x with respect to theta, because it's just our basic parametric equation, and this is how we find our derivative. Well, y's have to go in the numerator. Here you'll end up using the product rule, because you'll have theta here, and then you have this sine of theta. Well, product rule is really easy to use. So it's the derivative of our first term, so it's f prime of theta, times our second term, sine of theta, plus the derivative of sine, which is cosine of theta, times our first term. So I'm going to plug in the f of theta first to write that down first, times cosine theta. So really it's just, okay, take the derivative of this, product rule. The denominator then, obviously same thing, I have the product rule. The derivative of the first term is f prime of theta times our second portion here, which is cosine theta. We should be adding, but we can plan ahead and say, okay, well, I know it's the derivative of this portion, which is negative sine, times the first, or times that f of theta. So it's negative f of theta times sine theta. So really easy if you make it a parametric equation. And then you're not having to memorize anything new, and the formula is the same that we've been dealing with in parametrics. So I think that's a really nice part of it. To find a horizontal tangent, well, very logical. It's where your derivative is equal to 0. So again, our numerator is equal to 0. Our vertical tangents, when our denominator is equal to 0, great, set the denominator equal to 0. Here is one stipulation with this. If the derivative of y and the derivative of x are simultaneously 0, then we can't make any conclusions about our tangents. So if they're simultaneously 0, we can't say that it's a horizontal tangent or a vertical tangent. All right, so a couple examples with this. The first one is we want to find the horizontal and vertical tangents, and we have r equals sine theta, and this is nice that they give us the domain that we're going from 0 to pi. So that's really nice. So then, because we know that trig functions continue forever, this gives us, I guess, boundaries, which is good. So like I said, when you're trying to find your derivative, which we need our derivative to figure out our horizontal and vertical tangents, I would write this as a parametric equation. So what does x equal? What does y equal? Well, I know that x is equal to r cosine theta. Well, in this situation, r is equal to sine theta. So then x is equal to sine theta, that's going to take the place of r, times cosine theta. So pretty basic. Oh, I know that y is equivalent to r sine of theta. Plug in r, I know my r value is sine, so I have sine of theta times sine of theta. Well, that will just make that squared. Now to find my horizontal and vertical tangents, I can write out the entire derivative here, because I have to look that they're not simultaneously 0. So you're almost forced to do both of these things. Even if I just say find horizontal tangents, you have to also check your vertical tangents, because if they're simultaneously 0, it's not a horizontal tangent. So the derivative of y, well, here's y. So I have sine squared of theta. That means I'd have to use the power rule first, which would be 2 sine of theta based to the power of 1. And then the chain rule times our inside function, or the derivative of the inside function, so the derivative of sine is cosine. So derivative of y. And then in our denominator, the derivative of x. Okay, well, it's just our basic product rule. So the derivative of sine is cosine times cosine. Well, that will make it squared. And then it should be plus, but because I'm dealing with sine and cosine, I have a lot of negatives. So the derivative of cosine is negative sine. So it's instead of positive, I'm subtracting. Sine times that first portion, which is sine. Okay, well, there's sine squared. So derivative, super easy to come up with. Now if I'm checking for my horizontal tangents, so horizontal tangents, we know that's where our derivative is equal to 0, so the numerator would have to be 0. Well, where does 2 sine of theta times cosine of theta equals 0? This is nice because it's multiplied, so basically it's factored for you. So whenever sine of theta is equal to 0, we know this whole thing is 0. Or when cosine of theta is equal to 0, that whole left side is 0. And our domain, remember, is from 0 to pi. So when does sine of theta equal 0? Well, that's when theta is equal to 0 or pi or 2 pi, etc. But I know I'm just going from 0 to pi. When does cosine of theta equal 0? That would just be pi over 2 for that domain that's given. Then, next I have to check for my vertical tangents. And our vertical tangents are where our slope, our derivative, is undefined. So where the denominator is equal to 0. And we have cosine squared of theta minus sine squared theta has to equal 0. Not that this one is hard, but it's not quite as easy as that first one, because the first one you have multiplication, which multiplication we really, really like, because if one term is 0, we know the whole thing is 0. Here, we'll set these two things. I'm going to add the sine squared. And this isn't too difficult either. We should know when cosine squared is equivalent to sine squared. We know that these two things are equal, or sine and cosine are equal at 45 degrees. And because we're squaring them, it's always positive. Therefore, theta will be pi over 4 from quadrant 1, which they're both positive there anyway. But we do also get 3 pi over 4, and that comes from quadrant 2. Usually in quadrant 2, cosine is negative, but because it's squared, it's positive. And then in quadrant 2, sine is negative, but because it's squared, obviously that's positive as well. And we don't include 5 pi over 4 and 7 pi over 4 because that's not in our domain. So this is really nice. We don't have any parts where they're simultaneously equivalent to 0. And so therefore, to find our horizontal and vertical tangents, what I would say is my horizontal tangents. Remember when we polar coordinates, it's r theta, and these are theta values, so that would be 0. If we go in order, then it would be pi over 2, and we have pi. We have to calculate, if I ask for points, what our points would be. We can plug them back into our original equation, because remember the points have to be on the original. So sine 0 is 0. Sine pi over 2 is 1. Sine pi is 0. So there are 3 points where we have a horizontal tangent, Our vertical tangents, our theta is pi over 4 and 3 pi over 4. When we plug those back into the original, because we're looking for points on our original graph, sine of pi over 4 is square root of 2 over 2. And sine 3 pi over 4 is also a positive square root of 2 over 2 because sine is positive in quadrants 1 and 2. So pretty basic, nothing new. We've dealt with horizontal and vertical tangents for a very long time now. Last thing in this section is tangent lines at the pole. So remember our pole is at 0, 0. So here's our pole. And what this says is that alpha is going to represent an angle. So if you plug some specific angle into your function and that equals 0, and if you plug that angle into the derivative and it doesn't equal 0, well then the line theta equals alpha is a tangent at the pole to the graph of r equals f of alpha. It sounds confusing. It really isn't too bad, and after we go through this example, I think it will be pretty basic what it is. The first thing that we have to do is, what we want to do here, is sketch the graph of our polar equation. So here's f of theta, and we have 2 cosine 3 theta. And then after that, we want to find our tangents at the pole. So let's just review our graphing here. And when you graph, I'll almost always make you create a table for it. So we have theta, we have r, and remember when we're graphing, we always want to evaluate our quadrant angles. So I want to evaluate, 0 is easy because if I plug in a 0, great. I want to get 0. So 3 times 0 is going to give me 0. Cosine 0 is 1 times 2 will give me 2. So when my angle is 0, here's my angle 0, I want this to be 2, and I'm going to go by halves again, so that would be 1, this is 2, this is 3. Alright, so there's my first point. Now the next thing that I want to evaluate is pi over 2. Well, I can't just say pi over 2, because if I plug in pi over 2, that gives me 3 pi over 2. And I want to be evaluating specifically what is cosine of pi over 2. So if I want it to be pi over 2, theta then would have to be pi over 6. Because 3 times pi over 6 will give me the pi over 2. So you always have to think of, I want to evaluate pi over 2. What does theta have to be to evaluate pi over 2? Well, now I have, obviously when I plug in my pi over 6 times 3, I have pi over 2. Cosine of pi over 2 is 0 times 2 gives me 0. So at pi over 6, here is my radial line for pi over 6. And in this situation, because that's my radial line, I cannot cross it. So when I create this portion of my petal, you cannot cross that pi over 6. And that pi over 6, if you went way beyond it, that wouldn't be good. That radial line basically gives us the thickness of our petals here. The next thing that I want to evaluate now is pi, because that's my next quadrant angle. Again, if I just plugged in pi, I'm evaluating 3 pi. I don't want that. I want to evaluate specifically pi. So then I'd want to evaluate when theta is pi over 3. So if I plug in pi over 3 times 3, that's pi. And now you can see, obviously, we're changing by pi over 6 or 30 degrees. So when I plug this one in, I now have cosine pi, which is -1, times 2 is -2. So at pi over 3, here's my radial line for pi over 3. Well, this time, I have to have my point is -2. And how I'd be graphing this one, and don't draw these things in, but here was pi over 6 where we were, and I'm going to pi over 3. So basically, I'm between those two radial lines. So that's how, like if you're looking for the direction and how it was graphed, that's how it would go. All right, well then if I follow my pattern here, the next thing that I'm going to evaluate will be pi over 2. When I plug that in, I create 3 pi over 2. Cosine 3 pi over 2 is 0. Times 2 is obviously 0. So from pi over 3, which is this radial line, pi over 2, which is this radial line. Whoa, totally missed that one. Now, here is how I'm going to create that petal. The next thing that I would want to evaluate would be 2 pi over 3. And when I plug that in, that will give me cosine, well, let me back up, 3 times 2 pi over 3 will give me 2 pi. Cosine of 2 pi is 1, times 2 will give me 2. So at 2 pi over 3, and now remember I'm from pi over 2 to 2 pi over 3, so that means from here to here, I have to stick between those two. I have my answer is 2. So that will create it going that direction. Oops, kind of missed the first part there. And then the next point that I'd evaluate would be 5 pi over 6. 3 times 5 pi over 6. That will give me whatever it is. Cosine of that is 0 times 2 is 0. So I know here's my 5 pi over 6. There is that portion of the petal. And then the last thing that I do want to evaluate would be pi. Cosine of 3 pi would be -1 times 2 will give me -2. Well, pi, remember, goes this way, but if I want to go -2, that brings me back here. So this flower only has 3 petals to it. So that was our first part. We sketched the graph of our polar equation. Now we want to find the tangents at the pole. Well, to figure out our tangents at the pole, we want to know when does our function equal 0? And we want to figure out those angles. Well, once you've graphed it, it's really easy. We know that our function, f of theta, equals 2 cosine 3 theta. When does that equal 0? Well, it's when theta is equal to pi over 6, pi over 2, and 5 pi over 6. So that's really nice. It's easy once you have that portion of it. Or here, you know, you could, I guess, just evaluate it without having a graph. You could do it. It's a little bit harder. The other good thing about having your graph first, which usually I will make you graph it, is that you now know our domain, because it wasn't stated in the original. So we know our domain goes from 0 to pi. Well, in order for this to have a tangent at the pole, when you plug these values, the theta values, so I'm basically calling alpha, I'm just calling it theta instead, which is fine, it represents an angle. If these values if I plug them into the derivative and they do not equal 0, then the line, and this is why it's weird to say theta equals theta, but these lines would be tangents at the pole. So I have to take the derivative. Well, if I take the derivative of this thing, I don't have to do anything crazy and fancy with it. I can just take the derivative of this thing as it is. So I don't have to go back and use parametric in this situation. I just want this plain old derivative. I'm not finding slope with it. I'm not doing anything crazy with it. I'm not trying to take, you know, like derivatives, or I'm not trying to find the slope. So basically I can just take it as is. So then I would start 2 as a constant. I'm just going to leave it. The derivative of cosine is a negative sine. I have to keep my angle of 3 theta. And now chain rule, the derivative of 3 theta is 3. So when I multiply that by the 2, that gives me 6. Well, now when I plug in these 3 values into my derivative, so I want to evaluate what is my derivative at pi over 6. Well, that gives me negative 6 times sine. 3 pi over 6 will give me pi over 2. Sine of pi over 2 is 1 times 6 is equal to negative 6. That does not equal 0. Therefore, theta equals my original angle here, pi over 6, is as a tangent at the pole. And I have to just do the same thing with the other 2 angles. So plug pi over 2 into the derivative. So I have negative 6 times sine of, if I plug pi over 2 into this thing, I create 3 pi over 2. And sine of 3 pi over 2 is negative 1 times the negative 6. That gives me 6. Well, obviously 6 does not equal 0. Therefore, when theta is equal to pi over 2, that is a tangent at the pole. And the last one here, if I plug in 5 pi divided by 6 into my derivative, I have negative 6 times sine. Why am I having such a hard time evaluating this? 5 pi over 2. Sine of 5 pi over 2 is 1. So times a negative 6 will give me negative 6. That does not equal 0. Again, theta, when that's equal to 5 pi over 6, is a tangent at the pole. And if we check out what this means, if we graph these lines, so if we graph pi over 6, here's pi over 6. It goes through the pole, and it's definitely tangent to our graph. And so you can kind of predict these without even graphing them, or without even going through the work, but if you look at the graph, we know pi over 2, yeah, definitely. And then we have 5 pi over 6 Good, and we know we didn't miss one because your petals, all the petals, you're bounded between your two poles. So here my petals are bounded between them, petals are bounded between them. I found all of the tangents at the pole. All right, so here's the assignment for section 10.4. Good luck.